So I want to give just a quick introduction to Xiaolin. Xiaolin is a research scientist at JPL and one of the experts in microwave radar remote sensing in general. And she's going to be talking to us about a specific technology that they've been developing. And she took time to come out of her super busy schedule to come do this in person. So really appreciate you coming and welcome. And Xiaolin, actually, you did your PhD here? Yeah, so Xiaolin's a Husky. Go Huskies.
Yeah. Okay, let me fix this first. Okay. Can you hear me? Does that work? Okay. Higher. Where that work? Okay, let me change to my slides first. Okay, my name is Xiaolan Xu. As HP just introduced, currently I'm working at JPL in California. So I think I met HP probably 10 years ago when I was a graduate student here. And we work on one of they call like the CLPX3 project. So yeah, I definitely concur what HP has been said. So during the field work, you get to know people. And then throughout the year, if you stick into this area, you're gonna work all together to eventually, hopefully, like for some satellite mission. And this is also my topic, which is remote sensing technology for terrestrial snow using this is what we call P-band signals of opportunity. If you see some of the papers, you may see people talking about like SoOp, SoOp. That's the short for the signals of opportunity. So basically, this is kind of like a new technology started from JPL. And here I list 3 people, which is in the tutorial lead, Simon Yu and Raj Michel. So it's kind of generated from like one single idea from Simon. So he probably is the PI for most of the proposals. So this technology we have been developed about like almost 10 years since I started at JPL. So definitely this is not really a work for only 3 of us. This is a lot of work through the whole community. So at the beginning, I would like to acknowledge a few people. Some James Garrison from Purdue University. He is probably the pioneer in this field, the signal of opportunity, not only in P-band. I think he started as KU-band. But yeah, he's one of the pioneer professors in this field. Steve Margolis in UCLA, he is a professor working on the modeling part. And Chichi, he's a professor in Ohio State working on some of the hardwares. And a bunch of people in JPL developed the whole hardwares. Kelly Elder, he is a field person. I think a lot of people here know him. He's kind of the very early people who work in the in situ field and develop a lot of standards. How should you make the in situ measurement? So he also helped us with some in situ measurement to validate our data. And the last, Liang San from University of Washington, which is also my PhD advisor, working on some of the modeling part. So before I get into this signals of opportunity concept, I would like to know a little bit of my audience. Like, how many of you guys have worked with microwave remote sensing data? Okay, almost half of it. So, okay, so basically, microwave remote sensing data compared to the LiDAR data, the major advancement is this all weather, all day. So LiDAR is using basically the sun as the illumination. So you need to be in the daytime, and you also need to be cloud free, which in terms of snow application, it's kind of hard because like there are always storms that comes with the snow. So you will need to wait for some clear day to make the measurements. So that's one of the problem with the LiDAR stuff. And microwaves comes into play because it can penetrate through the cloud, and it doesn't really rely on the sun to have like a transmission. So usually for the microwave, there are 2 ways. They talk about active and passive. So for the active is you have some sort of instrument to transmit the signal, whatever frequency, like in the microwave band. Usually it's about like a few hundred megahertz to a few hundred gigahertz. So that's kind of the frequency of the microwave. So you have some kind of instrument that transmits the wave, and then it shines to the object. For us, it's the snow. And then you record the reflected signal in whatever direction, sometimes in the back direction, so that you only have one instrument in one place. You have shine the wave and detect the reflected wave. The reflected wave will have the information of the snow. The other way is called passive. So basically, it's just like a black body emission. You just receive the emission. And from this emission, you know the property of the snow. So this is kind of the major ways of microwave remote sensing. So this comes to our signals of opportunity concept. So basically, I will give a little bit introduction of that concept at the beginning, and then I will focus on P band, which is about like 300 megahertz frequency. So I will go through a little bit theoretical modeling for the snow application. So how can we extract the information from this received signal to get the snow information? What kind of snow information we can get from the signal we have from this technology we have? And then I will go through experiment and validation. So this is, I hope this can also give you an idea how a concept idea can be set up and validated through each of the stage and eventually push out for spaceborne proposal. So as just HB mentioned that there is a ESE, this Earth Explorer mission coming out. And this is one of the technology we hope we can propose and be selected so that we can have a way to detect the snow and also help the snow community to basically build up the whole information. So this is kind of the steps from the very beginning proof of concept ground experiment, which is around like, we set up that tower around like 2016. And then some airborne experiment we're trying in progress, and the spaceborne proposal, I will talk a little bit so that you can have a general idea. Finally, I will give a summary. Okay, so what is signals of opportunity? This sounds like a fancy name, but it actually just gives you the idea of there is some opportunities already existing in the space that we haven't used in the science area. So we have all the cell phone using the satellites. We have all the XM radio that you listen through your cars. And we also have some communication satellites for like military use. So all these satellites already exist. So you probably know there's a lot of satellites already existing for other uses. So the signal of opportunity is trying to just reuse this signal as a transmitted signal. So we don't really need to launch a new transmission satellite. What we need to do is build a receiver so that we can form a configuration, have a bistatic radar. So it's still like a radar concept, but the good thing for that is the transmit signal is already over there, and we are building the receiver so that the reflected signal can be received, and we can extract information from this reflected signal. So this technology has this a lot of beneficial characteristics compared to the active and passive technologies I mentioned before. So first of all, it is a high signal to noise ratio signal, because in this configuration, we have a forward direction scatter. So in terms of the signal that contain in this platform, it's easier to detect. So we don't really need very high sensitivity for this radar. So technology point of view is more reliable and easy to build. So that makes the cost can be lower. So as HB mentioned, for the Explorer mission, that's about like $400 million. And if you have a little bit general idea of like NISAR, SMAP, this radar mission, it's usually in the billion level. So this technology, one of the most important thing is it can be low cost. So the other thing is for this concept, we are detect the reflected signal, and we also have antenna receive the directed signal. So that makes easier to do the calibration. The other thing is the resolution. So usually when you compare to the traditional active and passive technology, the active are very expensive, but they give like a very high resolution. The passive is more traditional way of detecting the signal, but usually have like a low resolution. And for this technology, it's still kind of like a radar based. So it has kind of low cost, but high resolution. And the fourth advantage of this technology is some of the protected band, which has reserved for like communication or navigation, it's already reserved. So the band is very, it's already very, it's already being used by other technology. So in terms of science, you probably cannot use that frequency for science. But this technology basically use other region of signals. So it can use some of the protected band for science application. So that's also a big advantage to expand our frequency range. And it's not really affected by the RFI because we basically use other signals. So there's no RFI issue. So that's why we are looking into this concept. So for our SNO application, for our technology, we are focusing on the P band. So for the P band, the transmitted satellite is called MUOS. It's a US Navy communication satellite, and it consists of 5 geostationary satellites. So it has almost global coverage. And I will show a little bit about the coverage in the next slides. But here I have a table listed a lot of satellites. You may recognize some of them like DirecTV, Access Radio. This is something that we used to use. And also the GNSS, basically the GPS signal in the L-band. And some of you may also have some research in the GNSSR community. That's basically a whole community trying to take use of this GPS L-band to do some science application like snow, soil moisture, both land and ocean. And there's already like a satellite mission called Cygnus launched using this technology, but this is all in L-band. And in our application, we choose L-band. I will talk about why we choose, why we choose P-band in the later slides. But here I just want to give you an idea of what's the frequency band. So we are using about like 200, there are two frequency. At the beginning, they have like 200 megahertz for transmit. And now they slowly move to 300, which has much higher power for this 300 megahertz. So our frequency range is in that 360 to 380. And for this frequency, we have a deeper penetration. So usually you have longer wavelengths, and then you will have a deeper penetration. And in terms of the coherency, the lower frequency will more likely to be coherent wave. And the signal basically is pretty reliable transmission signal because the military uses for the communication. So we kind of expect it to be continuing a long time. And in this frequency, specifically for snow, this frequency, because of the long wavelengths, is less sensitive to the snow grain size. And this is always a difficult area for the radar technology, because that radar we're usually using X-band or Ku-band. It's very sensitive to the snow grain size. And for some of you in the field, you know, like snow grain size is very hard to measure, no matter what kind of technology we use. So it's always kind of like a tuning parameter in every part of the modeling. So if the whole technology is less sensitive than the grain size, it can help us eliminate one of the problems. So this is just give you a general idea of how this MUOS satellite is covered. So basically you can see it's covered up to about like 65 latitudes north and south. So it's not really can be used for some of the polar signs, but for terrestrial snow in most of the Canada, US, Alps, Tibet, this is a perfect technology. They have full coverage. And as I talked in the beginning, that we use P-band, but why? So this is a kind of a figure to show why we choose this P-band instead of L-band. So here we show 3 frequency. The XKU band frequency is usually the traditional radar snow remote sensing has been used because it's sensitive to the scattering of the grain size. So that's the frequency. And L-band is just, I mentioned, the GPS signal is in L-band. So there are a lot of technology has been built up for this signal opportunity for L-band. And then the reason we're choosing P-band is because we're aiming for the mountainous snow. And you can see as the slope goes up, you go top to the mountain, there are more and more snow. And you can hear, I have 3 image here that is showing in the East Sierra. And if you have only a little bit of the penetration, which expanded KU band, that's what you can see. So you only can observe some of the shallow snow and throughout the year. And then if you go L band, it will get a little bit deeper. But in the P band, you probably can penetrate all type of snow in like a few meters or more. So that's the main reason that we're focusing on the mountainous snow, and we hope we can have like a full range of the snow so that we can have basically the flashlight can go a little bit more of the area. Okay, so after I give this introduction for this concept, let's see how we can get the snow information from the reflected signal we detect. So this is give you a general idea how it looks like. So basically, we will have a receiver. One is facing to the satellite to have the direct signal from the satellite. That's more like GPS or this cell phone signal. You just receive the direct signal. And the other information is from the reflected one. So you can see, I'm not sure if this is, oh yeah, you can see my cursor. So one antenna is facing up and the other antenna is facing down. So the facing down antenna basically gets the reflected signal, which contain the information of the ground. Either you have some vegetation or you have snow or it's just bare soil. And for the different depths of the soil, that's all the information contained in this reflected signal. So what we do is we cross correlate between the direct signal, which basically the original signal and the reflective signal to estimate the time delay so that this part of the phase information will relate it to the snow. So in our case, this reflected signal has a phase delay here, and it's proportional to the speed and also the frequency. So this is kind of a simplified relationship between this. So you can see if we have a way to detect the path delay, the phase change between the reflected signal and directed signal, we can just convert it back to this way. So this is a theoretical concept of that. So for the snow case, we basically have 2 parts of snow. So at early stage, the accumulation period, we usually have like a dry snow. And then in the melting stage, we will have a wet snow. So the relationship between the dry snow and wet snow is also slightly different. So here, if we have a dry snow, because it's long frequency we are using, it can penetrate through the whole dry snow and bouncing back most likely from the ground. So the phase change is related to the speed change. And on the other hand, if we have wet snow, that means the wet snow, the permittivity is very close to the ground and maybe even higher. So the reflect surface kind of elevated from the air snow surface to the from the snow ground surface to the air snow surface. So then for the wet snow, you kind of have a different phase change, and it related to the snow depths. So here is a simulation that's showing the phase. The y-axis is the phase change, and the axis is the frequency. So you can see the phase change is related to the sway more in the dry snow region, and also with snow depths more in the wet snow region. So this is kind of the theoretical measurement approach that from the simulation. So to prove this concept, at very beginning, we set up a ground tower at freezer. So this is kind of a small set of experiment in the SnowEx. It's not in Grand Mesa, but still in Colorado. And this tower has been set up since 2016. And we're trying to prove the concept that I just introduced to see if we do build those two receivers, and throughout the year when the snow accumulates and melt, will the phase we detect same as we predict in the modeling, that it increasing and decreasing. So we have two sites set up over there. One is just the simple one that only have snow. We clear up the whole area. There's no vegetation, no trees. We choose like pretty much open area. And we have a weather station set up in the one of the corner, so that we know the whole snow depths and also wind, temperature, and everything. And the other side we set up is very close to that, but we specifically choose some of forest area. This is very common in the mountainous snow, that you have a lot of forest in a certain elevation. So in the previous technology, the forest is always a problem, that we have to eliminate the forest effect in the signal, so that we can get the information from snow. So we also want to try to see like forest in this frequency will have any effect. So we have two sites set up there. So here is one of the time series of the snow accumulation. So this is from 2016 data, and you can see the blue one is measured phase, and the red one on the right side is the snow water equivalence measurement from the in situ. So we are seeing a very good correlation between those two, and this is what we want to see. So basically, our theoretical modeling is proved by this simple concept at one point over 1 year. So this is not really enough. So we want to try to see if it is consistent over the years. So we have here in this plot, we have showing 2 years of the data. One is from 16 to 17, and the other one is 17 to 18. So actually the tower is still there. We're still collecting the data, but it's pretty big volume. All the rest of data we're still processing. But from this 2 years of data, we can see that using this technology, it's very, we can retrieve the SWE, and it's within the RMS here. Some of numbers you can see is linearized and very easy to do the retrieval. And the other thing is in the middle one, we have two, basically we have 4 colors. 2 from the vegetated area, the other 2 is from the non-vegetated area, and it's 2 frequency ranges. One is 200 something, the other is 300 something. So in both frequency and in both site, we can do the similar retrieval. Basically, the forest area in this frequency is most likely transparent. So we don't really have too much effect from the trees. And this is also one advantage to use a longer frequency. So the last one is the wet snow. So wet snow, basically, it's not really related to the SWE, but the snow depths more. So you can see this is a negative correlation, but it's also correlated with the phase. So that's kind of the tower measurement we have been done to prove this concept. So after this ground measurement, we're thinking like, the next step will be the airborne. So if we will have the same technology and put it on the airplane to have more area, we can have more variety of the snow and test this technology. So the other thing we have been done since 2018 is we're trying to use like a small UAV, and we design like a small antenna, patch antenna. That's very low profile. You can see the antenna is on the right side. It's about like this size. So it's we put them into like a UAV, which is more like a airplane, but it's very small. The airplane is like about half of the human size. So we try to do that, but unfortunately, this model is not stable enough to fly over like freezer area. So it's not very successful experiments, but that's the first try we're working on for the airborne experiment. So currently, we still kind of step back a little bit, trying to put this instrument in the traditional airplane, like some of the twin otter that SnowEx has been using. But yeah, that's kind of the progress, how you advance from the ground measurement to airborne measurement. And then at the same time, I'm also trying to do some spaceborne proposal, because this technology is really more advanced if it can put into the space, and it's really low cost. So we directly going into the spaceborne kind of competition. So the first one we submit, it is for the EVM. So EVM is like another way in NASA to promote some of the new technology. So we put this our proposal about like 4 years ago, and the thing is same technology. We're trying to use 3 satellites here to have some of the tracked over the mountains, so that we can get the snow information over the mountainous region. So to do this spaceborne technology with 1 point measurement is not really enough. So the modeling set coming through. So we've built an OSSES system to using some of the modeling from the hydrology model. They have some real analysis data to provide where we have snow and how the snow accumulate over the years. That's all from their modeling. We just use this as a ground truth to build up a whole simulation to see if this technology can work. So basically, we have this hydrology model to provide this snow information. And then we have a forward model to predict if the snow condition is here like that. With this technology, what kind of signal we expect it to receive. So we will some orbit information, we will some sensor characteristic, all put into this forward mode. So we have like so-called synthetic satellites data that used for us to simulate what we can receive. So then we use that to test our retrieval model and finally compare with the observation data. So that's the way without real spaceborne data, how you test your system. So, so this is some of the Swath simulation. So you can see with this technology, the Swath is not really very wide. So it's not a really full coverage of the whole globe. It's kind of Swath track. You will know a sample of information here, here, and here. And with that, you still need some modeling effort to like make the full coverage. So this technology, although it's spaceborne, it have like big sample, but it's not really like the NISAR or SMAP is like all imaging technology. So we still need to some data simulation technology to help us to fulfill the whole area. So this gives you an idea of how this technology works. And then, so this is one of the footprints that you expected to see. So for this setup, basically the resolution is about like 3 kilometers or so. And here I plot the DEM, the sway distribution, the forest cover, and incidence angle over this one footprint. So you can see in this resolution, it's still like a lot of variety between that. And this inhomogeneity of the snow will distract it, will basically provide a lot of noise in the retrieval algorithm. So it can be hard to have a very accurate snow because we only kind of have one reflecting signal over this whole area, and it will only give you just one number to represent this. And most likely it may not be just the average because it depends on where you are and what kind of topography you involve. It can be introduce a lot of error. So I will pass this. This is just some theoretical work. So over this OSSES system, we find out if we have include the whole Western US, a lot of places are homogeneous snow. We have a pretty good retrieval result and have a pretty low RMS error. But if you just focus, say, for example, in the East Sierra, there's a lot of rough terrain, then the result can be scattered around. So one thing of the technology we're trying to work on is if we can sharpening the resolution and give us more accurate results. So this is one of the projects we're working on. It's also supported by NASA. It's called Instrument Incubator Program. So it's kind of promotes the new technology. So what we have is, at very beginning, I said this is a bistatic radar setup. So to sharpening the radar signal, the most used for thing is the SAR processing. So we're trying to use the same data processing method in this bistatic configuration. So instead of have just one receiver, we will have an array of a receiver to extend the reflected signal and then do the SAR processing. The main purpose for this SAR processing is trying to sharpening the resolution and increase the accuracy. So still same thing. We have done like a proof of concept experiments basically at JPL just to use, you can see in this truck experiment, we have antenna here and we try to move the beam of this cherry picker to simulate multiple receivers. So here are some targets. So we're trying to see if we can do this SAR processing to sharpening the resolution. So this is something we're working on. And with the same concept, we're trying to do piggyback on some of the SnowEx flats over the Twin Otter. So instead of using the kind of experimental UAV small plane, we're going back to this airplane to try to see if we could use this technology to sharpening the resolution. So at the end, I want to show just like kind of a general map of all this technology has been using in the snow in this three-dimensional way. One is in the resolution. So as a lot of hydrology people know, in different resolution, it enable different science question. So if you have only have like a 10 or 50 kilometer of resolution, you probably can only do some climate thing. And if you go into the final resolution, you can really dive into more science questions that you can bring up and answer. So this is the current satellite we have. The very beginning, the IMSAR is the kind of the very beginning remote sensing satellite using the passive. And it gives about like 10 to 50 kilometer of resolution. And because of the frequency, the depths, basically the cube depths is around like very small because it's using higher frequency. And the revisit time is about like 3 to 5 days for the globe. So you can see for each of the missions that we have been mentioned, it's all here. And for the ASO, I think a lot of people have been using for this LiDAR program. It basically is not really spaceborne, but it frequently flew over some of the region. So it gives a little bit longer revisit time. And also it has a very high resolution. So you can see because it's the LiDAR thing. The problem is because this LiDAR is only sense the surface. So with this SnowEx SAR technology and other things, this is the regions we kind of targeted in. So we hope we can have like a higher resolution and a deeper penetration depth so that we can detect more deeper snow, and also provided kind of less than a week or maybe weekly detection over the whole winter so that we can catch each of the storm. So yeah, so this is basically conclude my presentation. So in this presentation, I gave a little bit introduction of this SoOp technology, and the way we're using that is to try to have accurate sampling of the SWE basically over the globe area, and focusing more on the mountainous snow. And the way we're doing that is we measure the snow, we measure the phase change and relate it back to the SWE change. The measurement principle has been demonstrated through like tower experiments, and then gradually into the airborne test. And also eventually we hope we can have a chance to launch some kind of satellite in the near future so that we can have more information and also prove this concept. Okay, so that's all. I can take questions. Thank you.
I have a question about the liquid water. As things start to get wet, kind of flip from doing SWE to snow dip.
Yeah.
What happens in that transition?
Yeah, so that's I think that's one of the problem, or we still have, we kind of need to have some other measurements to help us detect when it's wet and when it's dry. So one way we're trying to do is using the power. So throughout the whole presentation, I'm focusing on the phase. So the phase is related to the SWE, the phase is related to the snow depths. But also the other information we can use is the power. So instead of using some other ancillary data, which is also a way, so we can detect wet snow using other technology or other satellite. But within this technology, we also can use the power. The power between dry and snow can be very different. So that's one of the ways. But if you ask right in between, that when the snow have certain of the wetness, that's kind of the blurring area. That's it's kind of it's a little bit hard for this technology.
But essentially, the idea is that you go from bouncing soil.
Yeah.
To bouncing.
Yeah. So basically, if you detect the power drop down to a certain level that you think, oh, it's wet snow, then you kind of switch to the other method. But in between, I think there's definitely a week or so at least that's in the transition period, then the accuracy, the error will definitely increase. But I think throughout the whole winter, if you can really catch the snow peak, the maximum SWE, and also start detecting when the snow getting wet, this is already like a very useful information. So yeah. Sure. I think that's more like the hydrology question. So what we're trying to provide is we're trying to provide when the snow start melting and what is the peak snow we have. And then from other technology, you probably have other information of the soil. And then by providing this accurate information of snow, we hope that's one of the probably science questions you can ask and then try to do the research. So this is how the technology, so we are most on the technology side and trying to provide more information of the snow so that if you puzzle all this piece together, the snow, the soil, and then you probably can have you can have answer a lot of science questions like how the soil salinity correlate with snow. But first of all, you need to know how much snow and when it's start melting. So that's basically all this technology trying to provide to the science, to the hydrology scientist, so that you can have a lot of science questions and then really know more of the process of the whole like snow accumulation, melting, and about all this process. So. So yeah, so this MUOS satellites we are receiving signal is a communication satellite. So that's a military, Navy military used to communicate. So we expect it to be like last long. And right now, 4 of the satellites can cover the globe. So they have 5 of satellites on orbit. 1 is the backup. And as at beginning, they call it UFO. There's another name to that. And they continually launch new satellites to replace the old one. So this is also one of the uncertainty for this SoOp technology. You rely on other people for all this transmit signal. And this frequency, this transmitted signal we're choosing is from there. And generally speaking, I cannot speak for them, but generally speaking, I think this is probably a long-lasting mission. So it's just a traditional kind of two probe it's called hydro sensor, right? Yeah, we kind of stick that into 4 different levels from like surface about like 10 centimeter, 20, 30, 40. In the freezer site, it's a very rocky site. So at the beginning, we are trying to use a tube to have like a every 10 centimeter, but it's very hard to dig a hole into that because you always run into the rock. So we have to kind of make a big hole, kind of like snow pit, and try to find some area to stick into that tube. But that's the sensor we're using over there. So far, so good. So basically in the winter, I don't have it here. But if you're interested, I can show you some of the soil moisture data we have. So over the winter, it will drop down to a certain level and stay for like 3-4 months for the whole winter. And when the soil start to unfreeze, you can see the soil moisture catch some of the soil moisture and start going up. And it catch some of the rain events in the summer. So for us to indicate when the soil is freeze and when the soil is thaw, it's kind of enough. And you can also see in different layers, they are kind of behave differently. So that's what we are using.
Just continuing with any additional questions?
Yeah, sure.